Alright, this clip here we're going to talk about how oxygen is carried in the blood. So oxygen is a gas, so it might seem a little odd that it's carried in a fluid, but it can be. Oh, wrong slide, here we go. So oxygen is transported in the blood in two forms. Most of the oxygen in our blood is bound to the heme portion of hemoglobin, and the rest of it is dissolved in the plasma. Okay, and so the hemoglobin is part of your red blood cells. Okay, and each red blood cells contain hemoglobin, and each hemoglobin can bind for oxygen molecules. Okay, and that's how we carry most of the oxygen in our blood. So how much oxygen do we carry in the blood? Or maybe a better question is, what's the greatest amount of oxygen we can carry? Okay, because if we're talking about aerobic exercise, oxygen is important, right? The more oxygen we can carry, the more we can deliver, and therefore the more we can use to produce aerobic energy. We can do more work, and we will not fatigue at as low of an intensity. So the oxygen carrying capacity, or the greatest amount of oxygen that can be carried by an individual, is determined by two things. Okay? So primarily it's determined by how much hemoglobin you have. Okay? Because if hemoglobin is carrying most of the oxygen, then it makes sense that if you have more hemoglobin, you can carry more oxygen. So hemoglobin concentration, remember concentration is always represented in brackets, and hemoglobin concentration is represented as grams of hemoglobin for every 100 milliliters of blood. And some typical numbers for men on the average carry about 14 to 18 grams of hemoglobin in 100 milliliters of blood, and women on average are lower at 12 to 16. And we talked about that before. That's one of the advantages that men have with aerobic performances, is that they can carry more hemoglobin, or I'm sorry, that they have more hemoglobin and therefore can carry more oxygen. The other thing that determines how much oxygen you carry is oxygen saturation of the hemoglobin. So even though hemoglobin can carry 4 oxygens, okay, it's not always saturated with oxygen. So for instance, if this hemoglobin here was carrying, it can carry 4, but let's say it was only carrying 3, then we would say that this hemoglobin was 75% saturated. Okay, and so you need to have a lot of hemoglobin, but you also need to saturate that hemoglobin as much as possible. Well, most people have pretty well saturated hemoglobin. So normal arterial hemoglobin saturation is about 98 to 99%. It's not different for men and women, and it typically doesn't even decrease with exercise. Okay, in a healthy individual at sea level. When we get to altitude, saturation is going to drop. When you've got somebody with lung disease, saturation may drop. But in this class, this semester, we're always going to assume that we're talking about healthy individuals at sea level. So we got about 98 to 99% saturation under normal conditions. So again, in summary, the oxygen carrying capacity, or the amount of oxygen an individual can carry, is determined primarily by how much hemoglobin they have, but also by how saturated that hemoglobin is with oxygen. And that's called oxygen saturation. If you've ever had a surgery, they put that little red light on your finger, and that's what they're measuring. They're measuring your oxygen saturation rates to make sure that you're getting enough oxygen during the surgery. All right, talking some more about oxygen transport in the blood. Most of it is bound to hemoglobin. When oxygen binds to hemoglobin, it's called oxyhemoglobin, and it's written this way. Okay, so it's written HbO2, even though technically there are 4 oxygens there. We don't write Hb4O2, we just write HbO2, okay? Or there can be 4, right? If it's only 75% saturated, there would only be 3. All right, so when we're talking about hemoglobin binding oxygen, in the lungs, we need hemoglobin to bind oxygen, okay? Because oxygen is coming into the capillary blood, and we need hemoglobin to grab a hold of it and deliver it to the muscle. However, once hemoglobin gets to the muscle, we need hemoglobin to let go. Okay, we need hemoglobin to unload, right? So I usually use the analogy of a magnet. So hemoglobin is a magnet, and when the magnet is on, it attracts oxygen, and when the magnet is off, it lets go of oxygen. Okay, so there's certain times where we need it to grab oxygen, and there's certain times when we need it to let go of oxygen. So, what determines whether or not this magnet is on or off? Okay, what determines whether or not hemoglobin loads or unloads? Okay, so that's what we're going to talk about. All right, so unloading and loading of hemoglobin has to do partly with what the PO2 is in the plasma. So remember that oxygen is primarily carried by hemoglobin, but there is still about 2% of your oxygen that is dissolved in the plasma. And if the PO2 in the plasma is relatively high, which it is in the lungs, it affects unloading or loading. Okay, so first of all, let's step back and ask you, why would plasma PO2 be high in the capillaries in the lungs? Okay, so this plasma, we're talking about capillaries, blood in the capillaries in the lungs. The plasma PO2 is high. Why? Well, because that's where diffusion is occurring between the alveoli and the capillaries, and the PO2 of oxygen in the alveoli is relatively high, right? It's higher than it is in that venous blood coming into the capillaries, and therefore you're going to have oxygen coming into the capillaries, and as that oxygen comes in, you're going to have a high oxygen, high PO2 in the plasma. Okay? So if we look at it this way, and we're in the lungs, we're in a capillary in the lungs, and if the PO2 is relatively high, okay, and this goes back to mass action, this is in an equilibrium, and so if oxygen starts to come in and PO2 starts to rise, this is going to shift this reaction to the right. Okay? And therefore, hemoglobin is going to load oxygen at the lungs. Okay? We need it to load oxygen at the lungs. We need it to grab it and take it. Okay? And so then the lungs, the blood leaving the lungs is going to go into the heart. It's going to end up in the arteries. And that's going to end up in capillaries. And those capillaries end up delivering that oxygen to the tissues. Okay? And the tissues that we usually talk about are your muscle tissues. Alright, so now let's talk about what happens when this blood, the same blood, starts to go through capillaries in your tissues for instance, your muscles. Okay? Now, what we see in this dog fight again. Shh. So what we see in this situation is that we have low PO2 in the plasma in the muscles. Okay? So why is the PO2 in the plasma, in the capillaries, in the muscles relatively low? Okay? This is because in this situation, oxygen is leaving to go into the muscles to replace the oxygen that the muscles are using. Okay? So remember that the PO2 in this capillary blood coming from the arteries is higher than the PO2 in the muscles, okay, or in any tissue that's using oxygen. So if the PO2 is relatively low, okay, this is going to disrupt this equilibrium, and in order to replace that oxygen and regain equilibrium, this reaction is going to shift to the left. And when this reaction shifts to the left, hemoglobin unloads. Okay? And we need hemoglobin to unload because if that magnet did not turn off and let go, oxygen could not go into the muscle. Okay? So this magnet, hemoglobin is a magnet that is partly affected by PO2 in the plasma. Okay? So when the PO2 in the plasma is high, that magnet, hemoglobin, is going to turn on and it's going to load oxygen. Okay? But when we get to the tissues and there's a low PO2 in that area, the low PO2 turns that magnet off, okay, and results in hemoglobin unloading so that oxygen can then go to replace the oxygen that was being used in that tissue. So it's extremely important that hemoglobin is on, the magnet is on, so that it can load in the lungs, and it's equally important for it to turn off, for the magnet to turn off, and for hemoglobin to let go and unload that oxygen in the tissues so the oxygen can then go into the tissues. Okay? So PO2 determines whether or not hemoglobin loads or unloads. There's a couple other things that determine hemoglobin unloading. I shouldn't say determine, but affect it. Okay? Have an effect on whether or not hemoglobin load or unload. And PO2 is one, and the other one is what we call bonding strength, or the affinity of oxygen and hemoglobin. So what do they want to be together? Okay? And this affinity is affected by the pH in the environment where hemoglobin and oxygen are, and the blood in the blood temperature in the environment where hemoglobin and oxygen are. So I want you to think about it while I set this up. So what do you think is the effect of pH and temperature? So the effect of pH okay, unloading or unloading, or in other words, the affinity of hemoglobin and oxygen to hold on to each other, is called the Bohr effect. Okay? So what do you think happens when we have a low pH? Okay? Do you think hemoglobin is going to load or unload? Okay? And think about it in terms of exercise. What would make the most sense? Okay? So during exercise, muscles are producing lactic acid, and that lactic acid is giving off hydrogen ions. Okay? And so the more you exercise, the more hydrogen ion concentration you have, and therefore pH drops. Okay? So when you're exercising, pH is low. Okay? So what would you like hemoglobin to do when it's in an environment with a low pH? Okay? Hopefully you realize that we want it to shift to the left. We want hemoglobin to let go. We want it to have a lower affinity for oxygen so that it'll let go, so that oxygen can then go into the muscle. Okay? Because this low pH is an indication that something in that area is working. Okay? And when it's working, it needs oxygen. Okay? So the lower the pH, the lower the affinity hemoglobin has for oxygen. In other words, the more likely it is, or the easier it is for it to let go. And that works perfect with exercise, because that's a situation where we need oxygen to go into the muscle. Okay, and this is just going to be the pH. This is just going to be around the muscle. Okay, so during exercise, when hemoglobin and oxygen are in the blood in the lungs, okay, we're not going to see a drop in pH in the lungs because that pH is dropping in the muscle, not in the lungs, because the muscle is what's producing lactic acid. Okay, so the muscle is what's producing those hydrogen ions. Okay, so this is only occurring in the muscle. It's not occurring in the lungs. And actually the pH in the lungs is generally fairly high, which is a good thing, because we don't want hemoglobin to unload in the muscles. Unload in the lungs, because it's really important that we load it in the lungs, right? So the other factor that affects the affinity of oxygen and hemoglobin is blood temperature. Okay. So what type of temperature do you think is going to increase unloading or decrease the affinity of hemoglobin and oxygen? Okay. Under what circumstances would you want them to unload? Okay. Hopefully you guessed that when temperature goes up, hemoglobin is more likely to unload. Okay? And that goes together with what we've talked about, is when you're doing exercise, okay, the muscle's working. When the muscle's working, it's producing heat. Okay? And that heat is going to raise the temperature, and the temperature is going to make unloading more likely by decreasing the affinity of hemoglobin for oxygen, and therefore we have more oxygen available to meet the demands of what's going on, which is exercise. Okay? When you're not exercising, there's not a lot of heat coming out of the muscle. So unloading is less likely, which is fine, because when you're not exercising, you don't need as much oxygen. So it's all very logical, makes a lot of sense.